Hello and welcome to the Aryavat Center for Theoretical Physics. This is another lecture on the lecture series called Classical Field Theory. This is third lecture. In this lecture series, I am going to derive the Lorentz transformation. So, in the last lecture, I have explained the idea of interval and space-time diagram. Suppose there is a reference frame K, and we have assumed the coordinate of reference frame K is x, y, z and t, 4D space. Another reference frame K dash, which is traveling with velocity v, constant velocity v, and its coordinates are x dash, y dash, z dash and t dash, and it is traveling with velocity v with respect to k. Now, if velocity is very low, then we can use what we call Galilean transformation to connect reference frame K to K dash. So it will simply become x is equal to x dash plus bt, y is equal to y dash, z is equal to z dash, t is equal to t dash. This is called Galilean transformation. But in special relativity, there is a assumption or fact that C is independent of the any observer. It means C is universal constant. It means we have to accommodate this fact that C is independent of the object, independent of the observer, and also when velocity v reaches near to the speed of light, then we have to what we call change the what we call Galilean transformation. So transformation law in this condition will be different than Galilean transformation. How we find the correct transformation law for one reference frame to another reference frame? Now, there are two things which must be keep in mind. One, that the interval between two events, in the interval between events is simply nothing but a distance between two points in the space-time diagram. Distance between two what we call world points between space-time diagram, and this must be invariant under coordinate transformation. So we have two kind of transformation. One is called parallel transformation, another one is called rotational transformation. Now in the parallel transformation, nothing changes. We simply what we call shift the world points. We simply shift the coordinates of the world point. So nothing changes in case of parallel transformation, but real thing is rotational transformation. Suppose this is the x, y, this is x and y. Now we are rotating the coordinate system. It is becoming x dash and y dash. So rotation, the connection between this rotational coordinate system and this old coordinate system is x dash is equal to x cos theta plus y sin theta, y dash is equal to y cos theta minus x sin theta. Theta is the angle of rotation. This is for the what we call this is in case of rotational transformation. Now here take a look at this space-time diagram. This is the world line for the light, speed of light, and it is exactly 45 degree angle to this x coordinate. Now when any object reaches near the speed of light, we can show the world line as the hyperbola. This is the hyperbola because the space-time diagram for the object which is reaching the near the speed of light must be hyperbola. It cannot exceed beyond the speed of light. It means it must be hyperbola. So it means we cannot use the cos theta sin theta in this case. We only use what we call hyperbolic function, which is cos h beta sin h beta. Now cos h beta, here beta is the angle of rotation in this hyperbolic case. It means x is simply nothing but x is equal to x dash cos h beta plus y dash sin h beta, y is equal to x dash sin h beta plus cos h y dash. Now here y dash is nothing but a ct dash, because here instead of y we have wrote t, and here x is all three dimension of the coordinate x, y and z. Here is the fourth coordinate called t, and which will replace the y coordinate, and it is simply ct. So y dash is equal to ct dash and y is equal to ct. So it is simply nothing but a x is equal to x dash cos h beta plus ct dash sin h beta. Ct is equal to x dash sin h beta plus ct dash cos h beta, and here x is equal to ct dash sin h beta and ct is equal to ct dash cos h beta. Now we can use all these equation to find the correct what we call transformation law. Said that x is equal to ct dash sin h beta, ct is equal to ct dash cos h beta. If we divide these two equations, we will get tan h beta is equal to x divided by ct, and x by ct nothing but a velocity of the reference frame k dash. So tan h beta is equal to v by c, and we can use these two hyperbolic equation called 1 minus tan square h beta is equal to sec square h beta, cos square h beta minus sin square h beta is equal to 1. Here tan square h beta is equal to v by c. So 1 minus v square by c square is equal to 1 divided by cos square h beta, because here is the sec square beta. And finally cos h beta is equal to 1 divided by root under 1 minus v square by c square. This is for the cos h beta. Now we simply put this one into this cos square h beta minus sin square h beta is equal to 1, and we will get sin h beta is equal to v by c divided by root 1 minus v square by c square. Now we plug these two equation into this transformation. So we will get x is equal to x dash plus vt dash divided by 1 minus v square by c square, and t is equal to t dash plus v by c square x dash divided by 1 minus v square by c square, and these two are called Lorentz transformation. This is the connection between two reference frame. One is traveling with velocity v with respect to the k, and this is the transformation law. You can see that if v is much smaller than c, then whole equation, these two equation transform back into the Galilean transformation. So this is called Lorentz transformation. We can use the Lorentz transformation formula to derive what we call length contraction, volume contraction and time dilation. Here is the what we call Lorentz transformation. X is equal to x dash plus vt dash divided by 1 minus v square by c square, y dash, z is equal to z dash, t is equal to t dash plus v by c square x dash divided by 1 minus v square by c square. Now suppose there is a rod r which is at rest in the k reference system. Now end point of rod are x2, x1 and x2. So delta x, length of the rod is x2 minus x1. Now we can look this rod from the reference frame called k dash, which is traveling with velocity v. Now length of the rod is what we call invariant. It means it must have a same length in this reference frame too. So delta x dash is equal to x2 dash minus x1 dash. Now x1 can be written as x1 dash plus bt dash divided by 1 minus b square by c square. X2 dash is x2 is equal to x2 dash plus bt dash divided by 1 minus b square by c square. Now x dash for the length viewed from the k dash moving frame, x2 dash minus x1 dash, and it will simply become delta x is equal to delta x dash divided by 1 minus b square by c square. This is called proper length of the rod in a reference frame in which the rod is at rest, and this is called proper length. Now suppose delta x is equal to L naught. It means the rod which is at rest in the reference frame K has length L naught. So L is equal to L naught. L is equal to L naught root 1 minus v square by c square. This is called length contraction. It means the moving system will see the length of the rod has contracted, and same is with the volume contraction. V is equal to v naught root under 1 minus v square by c square. Now suppose there is a clock C which is traveling with this moving reference frame. It means in the moving reference frame clock is at rest. So delta t dash is equal to t2 dash minus t1 dash. 2 point registered by the clock in this moving frame, and t1 can be written as t1 dash plus v square by c square x dash root 1 minus v square by c square. T2 can be written t2 dash plus b by c square x dash root 1 minus v square by c square, and delta t dash is equal to t2 dash minus t1 dash. Now you can substitute t2 dash t1 dash and we will get delta t is equal to delta t dash divided by 1 minus v square by c square, and here delta t is the proper length, and this is called length contraction. Time dilation. It means moving clock appears ticking slowly compared to the clock at rest. So this is the derivation of Lorentz transformation and its application.